Hi, today we're going to talk about decision trees. Decision trees are one of the most simple classification methods, and probably you've seen them in previous classes. But we're going to review them here because there's some special things we want to say about them. So sometimes we don't have discrete features, we have rather continuous features. For example, suppose that we're worried about some package if it will explode or not. And suppose the data that we have about packages in the past gives us information about their mass, that is a real valued number, and the temperature at which we had them, which is also a real valued number. So, and for each one of those, we see whether it exploded or not. And really, there's only one case that exploded down here. So how can we represent this as a decision tree? Well, we might first check about the mass and say, is the mass larger than 8 or smaller or equal to 8? And in this case, we say if it's smaller than 8, then it's definitely not going to explode. Yes is if it is the mass is larger than 8. And then we want to check the temperature. If the temperature is larger than 500, then it might explode. Okay, so yes, no leads us to no explosion, and yes leads us to explosion. Okay, so these are two examples of a simple decision tree. In the continuous case, it's convenient to think about decision trees as partitioning the space. So here we have a two-dimensional space, x and y, and we're partitioning it using a decision tree. So the first partition is x larger than 3, which partitions the domain on a line that is x equal to 3. And then on one side, we have the prediction -1, so we're done here. And on the yes side, we check y, which is a split now on the y value, and then we get, if it's no, we get -1, and if it's yes, we get +1. This is a representation that is convenient. We'll be using it later to explain some other things. Okay. So why are decision trees so popular? Because they're very intuitive and easy to interpret, right? So if I give you a decision tree and you see what are the inequalities in it, it's relatively easy to understand what this tree is doing. Learning a decision tree means finding a decision tree with a small error on the training set. So basically looking for a decision tree that doesn't have too many leaves, that is not too complicated, and that has a small error on our training set. So how is this done? It's done in a greedy way. You start at the root node, you choose some splitter to put in the root node, and then at each step, you split one of the leaves according to one of the features. And you repeat this until you get to a termination criteria. So which node should we split? We want the children to somehow be more pure than the parent, right? We want, if the parent is very mixed, we want the children to be more pure than that. So for example, if the parent is 50-50 and the children are 90-10, 90 plus 10 minus, or the other child is 10 plus and 90 minus, then we have the children are much purer. So that's what we're looking for, rules that would give us that. But how can we quantify this improvement? How can we measure it so that we can compare different splits of different leaves? So the first naive approach that comes to mind is to minimize the training error. Okay, so just find the split that makes the training error decrease by the most. So here's a good case for this kind of rule. We have that the parents are, the parent node is 55 plus and 45 minus. So it always predicts plus, and the error that it has is 45%. And the children nodes are 90% plus 10 minus or 10 plus 90 minus. And this predicts plus on the left and right on minus on the right. And so the error is 10%. So in this case, the error has decreased nicely, and we're happy with what we have. But here is a case that is not so good. So suppose the parent node is 80% plus and 20% minus. That would mean that we're always going to predict plus, and the error is 20%. And now suppose that the children are 90% 10, 90% plus 10 minus, or 70% plus 30 minus. In this case, we still always predict plus, right? Because it's still plus is the more popular label both on the left and on the right children. And so as a result, if we're predicting plus always, we have exactly the same error. So there's no improvement in the training error. So it seems like this split has done something for us, but it is not giving us an improvement in the training error. So what we conclude from that is that training error by itself is not a sufficient criteria for how to choose a split. Okay, a different way to look at this problem with using classification error is to look at this graph that basically gives you, for every probability of the plus label, it gives you the probability of error. So over here, the probability is p, and over here it is 1 minus p. And what we get is this triangle. And it's a correct representation of the error, but it is also linear on the sides. And if you check the math, what you'll see is that means that if we have a node and we're splitting it, but the two children still have the same side as a majority, then we get no improvement in the training error, simply because the prediction in both children remains the same as the parent. To fix that, we need a different splitting criteria. And that's where we use something like the entropy. Okay, so entropy is this function that upper bounds the training error and is strictly convex. Okay, so basically the line that connects any 2 points is strictly below the curve, or any point along the curve. Okay, so what that gives us is that even if we are using the same, if we're splitting and the children are on the same side, we still can measure improvement according to this measure. So this measure does not get stuck in the same way as the training error. So it's not that entropy is the only one that can be used. Here we use entropy, but we can also use simply the circle, or we can use the Gini index. And each one of them has been used in the past in some way to learn decision trees. Which one of them is better is kind of up to debate. So the decision tree learning algorithm, as we said before, let's recap, is to find a tree with small error on the training set. We start with a root node. We split each, every time we choose one of the leaves to split according to our criteria, and we repeat until some termination criterion. So next, we are going to talk about how do we actually search for splitting rules. So I'll see you then.